Progress. Well, hello everybody. Welcome back. So today we're gonna first start with the two paper presentations that we didn't have a chance to present last time, and then I'm gonna continue giving a lecture. All right. So let's start with the first one. Please, guys, go ahead.
Hi everyone. Today we are going to present a paper named "Understanding the Faillight Attacks on Linux-based IoT Devices with Harney Cloud." I'm Jordan Wang.
I'm Juan.
I'm Tianyi, and we are all ECE graduate students.
Okay, firstly, I will describe the problem briefly. The faillight attacks on Linux-based IoT devices are on the rise, which pose a significant threat to the privacy to the IoT systems. So in this paper, the researchers want to understand and measure the faillight attacks in the real world in terms of the environment impacts and exploits. To better understand this paper, I want to introduce some useful background. The first one is Linux-based IoT attacks can fall into two categories. The first one is malware attacks. Malware is a software program or file that's designed to cause the damage to IT system or help the hacker to get access to the IT environment. The attackers have many techniques to install and launch the malware on the system. However, there are some solutions to handle this problem. In this paper, the research said they can calculate the malware's fingerprints based on the hash value of their binaries. And the second one is faillight attacks. Different from the malware, the faillight attacks will not leave any trace on hard drive. So they can take advantage of the weakness of the system, and the faillight attacks can bypass the existing security system and write the malicious code into the memory. So they don't need to download anything to attack the system. Unfortunately, there is few existing solutions for IoT devices because of the limited computing and storage resources. Finally, I want to introduce the honeypot. The honeypot is a technique that to deceive the attacker by deploying the baits like host and website services. To induce the attacker to attack on the system. So that the attack behavior can be captured and measured by people, which can protect the network from the current and future attacks. With the help of the honeypot, people can distract the attackers from real information and machines, and it can also prevent and build the vulnerabilities in a network system. And next, we will invite Tianyi.
So now we have understand the what are the background, like what are the faillight attacks, what is the honeypot, and why do we care about them? So now we want to understand the study methodology of this paper. So basically, the authors deploy a large network called Honey Cloud. So it is a system consisting of various numbers of honeypots across the world. As we can see in this overview, it consists of 8 public clouds and 108 software and also 4 hardware honeypots, IoT honeypots. And here are the illustrations of the hardware and the software honeypots designed by this author. And they actually conducted a year-long experiments to collect the real-world tech data. So the authors actually started with building the hardware honeypots, and then they found that due to some practical limitations, the hardware honeypots are actually costly and it's require pretty high maintenance overheads. Therefore, they started to think about the software honeypots. And as the software honeypots are pretty cheaper and much easier to maintain, they are actually much easier to be deployed at scale as well. However, as similar to many other engineering problems, there will always be a trade-off between them. And in this scenario, the problem is that although they actually built the software honeypots upon the insights from the hardware ones, and they claim that it could achieve pretty high fidelity, the software honeypots are still performing a bit worse than the hardware ones. And to be more specific, they actually attract 37 fewer suspicious connections and 39% fewer attacks than a hardware one. So they conducted an extensive analysis on the attracted attacks, and here is pretty considerable number of the attacks, and they concluded with this general working flow and also the categories of the captured attacks. So we can see that the flawless attacks are actually after the first phase, the intrusion phase, they typically set up forwarding and backdoors for later use. And it is also noticeable that although the software honeypots typically attract fewer attacks than the hardware ones, they actually contribute to 3 additional types of attacks other than the hardware ones. And the authors explain this. The reason probably because of the scalability of the network, because they have like over 100 softwares with only 4 hardware ones. And they conducted, they systematically categorized the flawless attacks into these 8 categories based on their behaviors and intents. And as we can see in this pie chart, as well as here, this analysis will be pretty helpful for further analysis as well as research into the regarding the attack behaviors. And it is also, so one thing is that although there are some attacks which are only making up a small portion of the attacks, they are actually not negligible, because the authors claim that these are pretty hard to detect as well as for preventing.
Yeah. So to evaluate the works in this paper, the researchers compared malware attacks and flawless attacks captured by hardware and software honeypot. And the results have been discussed by Tianyi, and the researchers also compared HoneyCloud and other related works. There were several criteria to evaluate the honeypot design, like fidelity, scalability, persistence, and containment. And it's said that in this paper, HoneyCloud could keep both high fidelity and containment. So then we can draw the conclusion that in this work, hardware honeypots and a large amount of software honeypots were built and deployed to capture IoT attacks. Then the data of flawless attacks was collected, analyzed characteristics and influences. In the end, the researchers also gave some suggestions about possible defense strategies. So after reading this paper, we can answer these 2 questions. The first one is that how to defend against the attacks on IoT devices. So it's suggested that we had better to use unique strong password and restrain the SSH service. Like the attackers will usually remotely attack the IoT devices through SSH service. The second question is that how to design a better honeypot. We could have machine learning based honeypot to make the honeypots more adaptive to the attacks. We could also make them open source to share the codes with others. In the future, we could do more things about machine learning based flawless malware detection, or designing scalable high interaction honeypots, and making deeper analysis and modeling of attacks. That's all. Thank you.
Questions? Did they mention, like, for example, you showed that table of like different kind of payloads? Did they mention what sort of data they're mainly targeting? As I think I saw 54% or something was mainly the data.
They also mentioned what kind of data would be the targeting, but it's not.
Yeah, if you go to the next one.
It's not typically relevant to different types of attacks.
But I mean, did they? So it seems that the system data is really the most interesting one for the attacker, right? Did they specifically mention which part of system data, or? did they provide any additional details of system data or not?
As far as I remember, I don't think they specifically.
But it's in it, so I mean, based on this, it seems like around 80% is some form of data analysis, right? Either stealing it or writing things to it, which is quite interesting.
Yeah. And the authors actually put an emphasis on the shell command thing. They provided pretty extensive analysis on the SSH stuff, and they said that probably because that this is really hard to detect, and just put more emphasis on this.
Hey, thanks for the presentation. So it seems like this methodology like really kind of looks at some of the more like low bit hackers. We're just kind of running, scanners to just find any random like IoT device and automatically own it if possible. Is there? Did they do any analysis of like anything more sophisticated than that? Like something an actual ransomware group would deploy, or was it mostly just like kind of the low bit stuff?
I would say the most contribution they made is first they built this large system as well as the hardware and software design, and the second one is that they collect this pretty extensive a large scale data set. Yeah, that's a key thing.
Yeah, so what I also understand, it's mostly like more of a data set penetration rather than going deep into each different types of. But yeah, definitely follow-up work could be like looking at particular types. Another question.
Yeah, so I also read this paper, but like I don't know if it was something I missed, or maybe they just didn't, I don't think they did a great job of, was like for like next steps with defensive. The suggestions were like use a strong password or like don't let people SSH into your system. It seems like rather obvious. You know if there's any like more research about possible defenses, I guess, because I don't think they did a super thorough job.
You mean the defense strategies?
Yeah.
More like basically most of the IoT devices passwords, they are really simple and like maybe the similar or the same. So like it's necessary to use unique strong password, and then like most of the attacks are based on the SSH service. So it's better to restrain the SSH service in the local area network instead of the like the wider network.
But yeah, there is no, I mean, as she said, I mean, the password issue is such a like very trivial but very important problem. That really, if you use better password, most of these things will be gone. But I mean, what we can do is like essentially the entire research area of like how we can make systems better. There's all this, we have all these techniques that we discussed around, making the memory corruption less, writing better code, make sure your code is not, vulnerable to corruptions, detection mechanisms such as, stack canaries, etc., etc. These are all basically solutions for this.
Okay.
But I mean, the first line of defense is that the network's not. Just use better password. Just don't open your SSH to do the open internet. Make it, tier system such that your network is an internal network. Then there's another network that is kind of connected to yours, and then maybe have better firewalls there, things like that. So
Yeah. All right, thank you.
Yeah.
I think when I read the paper, they mentioned something about making some file systems writable so that the shell code could be logged, so that they could see what kind of shell commands have been used and detect files attacks, but making those files writable enable malware attacks. Do you know what? If there has been any research done on this trade-off between making those files writable and enabling more malware attacks and trying to prevent to detect IoT files attacks using it?
Yeah, we didn't really look into the specific research into that, but that could be an interesting thing that we may want to look at it later.
I think they were intentionally creating the honeypot, so they wanted to actually have an infrastructure that they can log things, not necessarily in real systems you may want to do that, right? So that's a little bit different. What they've implemented versus what you're gonna have in real system is slightly different. Because they wanted to kind of log and collect all this different information as in like what would happen if the systems actually gets attacked. And they don't care about their actual data because it was all fake data that they put in their servers. So that's kind of like a little bit different than what you would get in real systems.
Okay, I think they had mentioned it in the defense strategies for fileless attacks, but I was thinking that if you are, since the malware attacks have so many more, doesn't make sense to allow more malware attacks to happen to defend against the fileless attacks. But I can't look into it and
Sure.
why.
I see what you mean, like, defense against ones might make the other one more vulnerable, probably, sure. I think it also depends on which one you are more vulnerable to, and then you probably pick the defense that is more effective onto that class of attack, right? So that's also another thing. But yeah, I think the details we probably can talk more. Maybe post it on Canvas where I am, we can take a look. Thanks. All right, thanks to the speaker one more time. Good job, guys. Thanks for accommodating. All right, so group 3. Okay. All right, let's do the next presentation then.
Okay, hi everyone, happy to be here, having another presentation on another sunny Los Angeles day. We're doing our presentation on jump-oriented programming, a new class of code reuse attack, which in simplest is another method of code reuse attack. My name is Darian. I am a master's of CS.
My name is Vincent. I'm also a first-year MSCS student.
And I'm Aditya. I'm also a first-year MSCS student.
Okay, so first, I'm going to talk a little bit about a problem and the current background, so we get a little bit of an understanding of the reasoning behind why we want to use jump-oriented programming. So first, of course, we've already gone this before, but we have the idea of code injection attacks, which is one of the earliest known software exploits methods. And in essence, when you look at it, it's essentially a message that is used to direct the control of the flow to the specific attacker's malicious code. And this message can usually contain some sort of machine code or some sort of buffer overflow that will mess with the system. So, of course, currently we already have some known injection defenses for this. And one of them, of course, is the write or execute guarantee. And another one is stack canaries, which we did discuss about later in class or early in class. And because of that, adversaries and attackers have found different methods and ways to essentially attack the system and gain control. Another one is, of course, code reuse attacks, which we haven't talked about before, which is used to exploit methods such as buffer overflow, which we could talk about, and to overwrite the stack, which can lead to the execution of certain functions with malicious parameters. And specifically, this paper goes around talking around return-oriented programming, an alternative for return-oriented programming, which essentially takes advantages of the ret opcode when using these operations, so that's able to jump anywhere within stack. Okay, and now, of course, there are already certain ways that we can account for ROPs, return-oriented programming. One of them, and most of them being that we essentially gain control by making sure that these return instructions are not being executed as much, or we have a measurement that allows us to count the amount of measure returns instructions, or in certain cases, we just fully not allow any return instructions, which unfortunately does mess with the system in many ways. And as you can see, most of these methods are in accordance with affecting with the stack. And now the overall threat model for this paper is that we assume that the adversary can insert some sort of payload to the memory and gain access to the registers, such as the IP registers. And we are deeming this as reasonable attack for the idea that buffer overflows and system will always be a problem.
So this sort of begs the question, what sort of code reuse attacks can we still do? As Darian mentioned earlier, we already have ways of detecting when a stack is being messed with. So the answer to what kind of code reuse attacks that we can still do is attacks that have little to no reliance on the stack, and particularly attacks that have have little to no effect on the stack's control flow. So that here comes the contribution of the paper, which is actually called jump-oriented programming. So jump-oriented programming is a new alternative attack that has no reliance on the stack. So as a result, it is immune to the defenses that are typically used for a normal return-oriented programming attack. So here's a little table that's actually comparing return-oriented programming and jump-oriented programming. So these are the main differences between the two, but as you soon see, they're actually quite similar. So return-oriented programming, the gadgets that you have, as you can see here in the gadget catalogs, for return-oriented programming, they end in return, whereas for jump-oriented programming, they end in jump or call statements. And for return-oriented programming, you'll actually use this the stack's program counter, whereas for jump-oriented programming, any register can actually be used as a program counter. And this is like something called the virtual program counter, which is housed in the dispatcher gadget for jump-oriented programming. That's a pretty big deal, and we'll be talking about it more in the next slide. And finally, probably the most critical difference between the two is that control flow for return-oriented programming is actually driven by the return instruction and actually overriding the return address that you're going to go to. Whereas for jump-oriented programming, control flow is driven by this dispatch table right here, and that is loaded into memory. Darian talked about this being one of the assumptions that we have for our threat model. So here's an example of jump-oriented programming attack, and these are the three different types of gadgets that are actually used in jump-oriented programming. This diagram up here highlights two of them, dispatcher and the functional gadget, but let's first talk about the dispatcher gadget. So the dispatcher gadget, as I mentioned earlier, serves as the virtual program counter. And something that's really cool is any lines of any instructions with a form of some function happening to the program counter and then going to that program counter can actually serve as a dispatcher gadget. So it's pretty much anything that can change the program counter in a predictable way. And the goal of the dispatcher gadget is to launch the functional gadgets, as you can see up top. And the functional gadgets are just something that conduct a simple operation. And something that another important consideration is that functional gadgets must actually conclude by jumping back to the dispatcher. And finally, something that's not included on the diagram is the initializer gadget. And that pretty much just gets the user's program to point to the dispatcher gadget. And from there, we can actually launch our attack. So this is a little bit more in-depth look into the actual attack itself. So at a very high level, what's happening is we're taking the values of EAX, sorry, not that column, EAX and EBX, summing them together and moving them into ECX. As I mentioned earlier, in the dispatcher gadget, EDX sort of serves as the program counter. And then when we add 4 to it every time, we're going through each address in the dispatch table. And something else that's important to consider is ESI and EDI, as you can see on the gadget catalog, sort of serve as a way to return the control to the dispatcher. And when you do jump ESI, that's called a direct return, whereas EDI is called an indirect return. And as you can see, JOP is actually very similar to ROP, except we're using a dispatch table as opposed to modifying return addresses. And finally, the last thing I'll talk about very briefly is how to actually find these gadgets that you're going to be putting in your gadget catalog. So at a very high level, we're scanning for 0xF, 0xFF in our binary, because that indicates there's a jump instruction, an indirect jump instruction. And the rest of this isn't really that important. Even this algorithm isn't that important. What's interesting to note is that there's been a lot of work done in recent years to actually automate the process of finding these gadgets, such as this cool tool called Job Rocket that eventually we'll talk about later.
Great. So now that we kind of have a brief background on how jump-oriented programming works, we kind of want to dive into the evaluation and see an actual attack be launched. But before we do that, we'll talk about finding gadgets. So they tested this on a Linux system running Debian, and this paper was published in like 2011. So they're running a 2010 version of Debian. which is a pretty common thing anyone can get. And they were able to find gadgets from the libc library, which also just comes with the system. So if you take a look on the table at the right, they were able to find 12 different dispatcher gadgets, which are used to launch the attack, and over 2,000 functional gadgets. And these are elementary instructions like add, subtract, load, and that kind of stuff. So in terms of the actual attack, they do run a shellcode attack. And essentially they use the set jump exploit present in C to load the thing. And just skipping all the details, they're ultimately able to launch an interactive shell at the very end. Now you're wondering what's so bad if they're able to run an interactive shell. Well, as we've discussed in class, it essentially gives them unlimited programmability, right? They can access your entire system, the files, the programs. And the danger of this attack is the ability for it to create a completely new attack surface. So traditional attacks are return-oriented programming, and traditional defenses work with the stack. However, with jump-oriented programming, it's a completely different attack surface. So some of these suggested defenses are things we've already talked about in class. We have stuff like ASLR. If you randomize the address space, you can't find your gadgets to use in your attack. There's things like control flow integrity. So you only want legal and valid executions of your program. And there's also things like gadgetless binaries, which kind of takes it a step further and removes these unintended gadgets and protects existing ones. So as mentioned, this paper was published in 2011. So the authors in this paper do suggest trying with fixed length instruction sets. The evaluation was done with x86, which has variable length, and it's easier to find gadgets that way since they kind of like chop off various parts to find their gadgets. Some later work within like the rough past 10 years, there's been various defense mechanisms like drop alarm, HCFI, and pack it up. They all use different forms of defending against drop. And there's also the most recent work called drop rocket, which prevents drop attacks and finds gadgets. Some of the discussion points we had, the first one was the paper mentions that it's a complex task to find gadgets and assemble this code. So we're wondering how complex is complex, right? Because obviously a really hard to launch attack isn't going to be that feasible. Second, is it possible for a JOP to be limited in a system that has limited jumps? So if the system doesn't even have that many jump instructions in the first place, can we still use this attack? And third, there's something called opcode splitting, which I mentioned is where they find gadgets from variable length instructions. So in x86, is it possible to eliminate this possibility? And that's all we have for discussion points. Thank you very much.
Thank you, guys. Questions?
Great job with the presentation. Could you talk a bit more about Job Rocket? I'm just curious how it does.
Oh, so I found this YouTube video of some PhD candidate who created Drop Rocket. So Drop Rocket pretty much just generates jump-oriented programming exploits given a fully linked binary. And based on like whatever gadgets you can find, the goal is by finding these gadgets, you can find some way to defend against them. So it doesn't really automate the process of defending against these gadgets, but it makes you aware of them so you can sort of figure out how to not run into them.
It's an open source code, right?
I think so.
Yeah, I can actually run it if you want to.
Can you conduct all the same attacks that you normally would with ROP but with JOP, or is it like a subset of the attack that you would normally conduct?
You can do all of them. I think you guys can actually speak more to this. You can conduct all the attacks, but the issue is it's actually harder to conduct this attack than a return-oriented programming attack.
Yeah, like return-oriented programming, JOP is Turing complete, so it'll do anything, but like you said, it's just harder to like launch your attack and stuff.
Only benefit is you won't get detected with the current detecting system.
Yeah. It's a trade-off. It's harder to pull off, but if you do it, then it's harder to detect as well.
You had a question earlier? Yes, yeah, I don't know. I thought you said you raised your hand.
Oh, no.
Oh, okay, that's my
Oh,
bad.
great presentation though.
Oh, I appreciate it.
Any other questions? About your discussion points, anybody wants to chime in? Any ideas? Yeah.
I have a question about the second point. Aren't the gadgets found in libc, so aren't you using those to make the jump-oriented programming? So if you design the code of the non-jump statements, wouldn't they find anyways from. Like they not understand how jumping and program works.
So you're saying removing the jumps in your program? Or what?
If you design code that does not have many jump statements, you still find the jump statements in libc.
Yeah,
To use them.
you can find jump somewhere else. So they need the initial gadget, which is essentially just exploiting the original code. Once you find that, then you jump to your dispatcher, which actually essentially where all these, addresses for those jumps are. And the rest is just, jump back and forth between them. The difference is in return-oriented programming, you use return, right? So all you need to do is really pushing addresses into your stack. That's all you need to do. Because once you do return, you just go back to the stack. But since you're not using returns, you use indirect jumps. So you kind of also need to keep track of where the jumps is happening. So you're kind of like jump back, check the register, then jump again, and so on and so forth. But keep in mind that we always need to have indirect jumps in our programs, like switch statements, function calls, if then else's, many of these uses indirect jumps. So you cannot really get rid of indirect jumps in your programs because that makes your life really hard as a program. So it's kind of like, it is what it is kind of situation. Does that make sense?
Yes, so is it possible to intentionally design code to not have jump statements?
You can design a program that doesn't have jumps. But two things to remember. One is basically you need to design a program that doesn't have bugs. Okay. That's really what you want to do as a designer. Because jumps, they can find it somewhere else in the code. For example, they can go to libc and find this jumps. What you really want as a programmer is not having bugs, but then it's like 1,000 lines of code and bugs are inevitable, right? So that's the really the problem. It's not like everybody is not paying attention to these things and say, okay, yeah, let's forget about this. It happens as a result of running complex programs.
Great presentation, by the way.
All right, guys, thank you so much. Okay, so that's kind of a good summary of discussion that we wanted to have for memory security, memory corruption and all those things. As you see, this list of papers that we discussed, all talking about various aspects of memory corruption, right? And you see that we start with like a simple buffer overflow, and we talked about return-oriented programming, and the papers that we seen in the past two set of presentation was essentially making things a little bit more complex, right? And kind of state of the things right now is all these different ways of attacking the system is really what you're dealing with. And as I just said, unfortunately, the problem is not like, we intentionally create bugs. It's just that this process of writing complex software ends up with a code that is very buggy, okay? But of course, there are also other ways to fix this problem, including using programming languages that are not, naturally vulnerable to this type of attacks, right? Like things like Rust that is getting a lot of momentum these days is one example. But generally, we are also dealing with lots of legacy codes, right? Like, for example, your Linux operating system is written in C and C++, and nobody gonna rewrite this in Rust anytime soon. So we are kind of you have to deal with this problems anyway. Okay. All right. Any questions about things that we discussed? All right. So let's go back to the discussion we started last week about side channels. So I want to finish that discussion today so that starting next week we can talk about the new thing. So if you remember, I told you that we have different types of side channels, and these side channels are just the opposite of what we discussed so far. It's the impact of the computing world to the physical world. I said that there are a bunch of different types of side channels, including power, electromagnetic, temperature, and so on. There's analog and digital. We're going to talk about the analog. We're not going to have time to talk about the digital one. Caches and transient execution attacks and so on. These are very interesting digital attacks as well. But that's, for some other time. So we talked about, what is the goal generally in these attacks, either physical or digital. The goal is usually kind of extracting some sensitive value. This value is usually a cryptography key that we want to find. Then we kind of talk about various different types of attacks. We start with what we call a simple analysis, which essentially was more of like a visual analysis of the code. I gave you some examples. For example, RSA. Early versions and unsecure versions of RSA is vulnerable to SPA's simple, power analysis. You can easily see that, you can see different phases in the program. Some phases is, square multiply, and some phases are multiply alone. And essentially by seeing that, you can tell whether the bit for the E, which was the secret key, was equal to 0 or equal to 1 by just looking at the pattern that you're seeing in the signal, right? And this pattern can be seen by anybody, right? So that's kind of like the problem that we're having. You can also expand it to other codes, including like things like ping. You can look at the different rounds in your crypto algorithm and so on and so forth. And then we said that this is generally what happens in 90s and early 2000s. People have seen that this is actually a big problem. So what they did was making their system robust against side channels. So most of the cryptography algorithms are designed such that they are actually robust against at least simple analysis. Okay. So these days, if you run AES, you cannot really tell the difference between 0 and 1, or if you run AES, there are things like masking and so on that actually kind of protect it against the simple analysis. Then we said that there is actually a more sophisticated attack called differential power analysis, that if I see the signal, I don't really, can extract useful information out of it. But if I create this slightly more complex algorithm, then all of a sudden I will see what I need to see. Right? So how did we do that? We essentially, using this algorithm that we are saying that, okay, we don't know what we are looking for, but we're going to deduce this strategy that we're going to make a decision. And if we make that decision correctly, I'm going to see the difference. So I know that at some point I will see the difference. I just don't know where, and I just don't know how. So what I'm going to do is that I'm going to brute force through different possibilities. And only one of them will give me the answer that I know that's the answer. I'm going to see a big difference between the signals and say, that's the right key, right? So essentially, I gave an example for triple DES. I said that essentially we started with saying, that, okay, I just want to know whether this last bit is equal to 0 or 1. And during this process, I'm going to find what this key is, okay? So that's kind of, an indirected attack. So what I'm going to do is that, I gave you the details. I know this, then I know this part. Then I'm going to start assuming various numbers for my keys. I'm going to, let's say, for example, this is an 8-bit number. So there are 0 to 255 different possibilities, right? Different numbers. So I'm going to brute force. I'm going to, go through these numbers one by one. I'm going to start with 0, 0, 0, 0, right? I'm going to say, okay, what if the key is equal to 0? Then I'm going to have this number. Then I have already this number. Then I'm going to have this number. So since I have this number, I know what is the last bit, whether it's 0 or 1. Okay. And based on that, I'm going to partition the signals into two groups that belongs to the last bit equal to 0 versus the groups that the last bit is equal to 1. Okay. And I'm going to repeat this for lots of random messages, okay? I'm not going to do it for one. I'm going to repeat it for many, many random variables. So it's such that I'm going to see the average behavior, okay? So what I'm going to see then is then I will have two groups of signals, those that belongs to 1 and those that belongs to, 0, and then those that belongs to 1. The idea is that if I average this, and if I average this, and if I subtract these from each other, if I really, partition this and classify this correctly, I should see a difference at some part of the signal. Why? because everything in this signal and everything in this signal is the same except for one bit. And I already told you that if there is different bit flips, there should be different signals, okay? So based on that assumption, I should see a big change at some point in this signal, okay, this time domain signal. If I see that, it means that I categorize these two groups correctly. If I don't see that, it means that I just randomly put something here and put something here. As a result, I should not really see any difference, because if you randomly, distribute two random variables, their average would be equal to 0. Okay, this the difference between the averages. Okay, so that's really the idea of how do we know that our key assumption was correct? Because remember, we started this with key was equal to 0, 0, and we do this. We're probably going to see that this is the case, not this one. So it means that this assumption was correct. It was incorrect. Okay, so what we do next? We go with key equal to 1. We repeat this process. We see whether this is this one or this one. What will happen is that we're going to repeat this all the way to 255. And there will be only one of these numbers that are actually going to give me this. All the others going to give me that. All right. And that would be the key that I'm looking. Okay. So this is kind of like an iterative process that I'll go through. And what would happen at this point? If you look back at here, it means that now I have this value here. So this I know. Then I can go one step before and then repeat it for keys 15 and key 14 and so on and so forth. So then I have the full key. Okay, this is how I'm gonna basically kind of divide and conquer approach. I'm gonna like go byte by byte of the key, find the key, and then go to the next one and go to the next one. Okay, so this is what we call the differential power analysis. As you can see, what we are assuming here is that I basically see this like quite complex signal. I have no idea where should I look for, right, for the signal. But what will happen is that at some point there is some correlation between various different parts of the signal and the values that we are actually, processing. And there is one point that there will be the big change between the two group of signals. Okay, so that's kind of the idea of differential power analysis. Any questions about that? Is that clear? All right. So, and then this is kind of, as I said, this is kind of a summary of that, different groups, different keys. There will be a big difference somewhere, and that's where you're going to know that you made the right assumption. Okay. So that's to summarize, what's the difference between the SA, simple analysis, and differential analysis is DA helps you to find those non-trivial cases that you cannot really visually see the differences. And usually what you need is a combination of both, because you probably want to, for example, know when a particular event is happening, and then launch your differential analysis attack on that. So usually in real attacks, you see a combination of both of them at the same time. Okay, so these are the first two approaches. There's another one called template analysis. So we're going to talk about that in the next few slides. So what is the template analysis? So essentially, when people start realizing that their systems is vulnerable to the various different side channel attacks, they start designing algorithms that are robust against simple analysis. And later on, they figured out that they also need to be robust against differential analysis. So we're going to talk about the defense mechanisms later. But for now, assume that you actually can have mechanisms that also, robust against differential analysis. Okay, so what the attacker does next is finding a new method to attack the system, and that's what we call a template analysis. The template analysis is based on this fact that we can, find an exact copy of the model that we're trying to attack. Okay, you can find an exact copy, for example, of the hardware that we're trying to attack. If you're trying to attack a cell phone, like an iPhone, then maybe you can go and buy an actual iPhone, same model, same version, etc., etc. Okay, then what you're going to do is that you're going to basically run some form of a data, like large scale data kind of base attack. Okay, so you're going to basically use something very similar to the way that our complex machine learning algorithm works. So you're going to collect lots of X and FX pairs. Remember, I told you, for example, for AES, right? What are we doing is we send X, which is our message, right? And then we have the key, and then we're going to get the ciphertext, right? So for X1, we're going to get ciphertext 1. For X2, we're going to get ciphertext 2, so on and so forth, right? Lots of them, okay? Till CN. And then for all of these, of course, the key would be the same, right? And the goal is we want to find this key, okay? So what we're going to do is that since I'm the owner of this device, I still don't have access to the key, or maybe I am, doesn't matter. What I'm going to do is that I'm going to collect lots of these X and FX pairs, all right? Then what I'm going to do is that I'm going to say that I have no idea what the key is. But what I can do is I can approximate this model with some model, okay, with some template. All right. So I'm gonna create an F test that if I see, for example, Y, if I get Y, I can tell what is K. Okay, it's very, very similar to, for example, the way that you design a classifier for machine learning, right? So what you do is that you have a bunch of different faces and a bunch of different labels for that, right? You don't know exactly how these two are matched together. So you're going to train it like, a deep neural network or a multi-layer perceptron, et cetera, et cetera. And then the next time that you're sending a face to this classifier, they're going to give you the label. Okay, so we're going to use the same idea here. All right. So for example, let me give you an example of just intuitively how this works. So let's say, for example, we have a list of signals that I'm showing here that is for a branch. Okay, so let's say, for example, we have an if then else statement, some instruction here, some instruction here. Okay, and then this is based on the key. Okay. So if key is equal to 1, take the if key is equal to 0, take the E and the else, okay? So what I really want to know is that by seeing this pattern, I need to really know that whether this is a taken branch or whether this is a not taken branch, okay? So what I'm going to do is that I'm going to run lots and lots of these pairs, and I'm going to collect lots of these signals, okay? For example, the blue ones are when the branch is taken. The red ones is when the branch is not taken. As you can see, they're kind of similar. There are some small differences. Then what I'm going to do is that I'm going to get this signal during the actual attack. And then I'm going to run through this different, signal, samples that I have in order to see which one is the one that I'm looking at. Okay, the one with the highest correlation would be kind of like the one that I'm looking at. Okay, this is a simple signal processing analysis. But one thing I could do is that the second thing that I can do is that I'm taking this signal. This would be, for example, think about this as a vector of numbers like A1, A2, A3, all the way to AN. I'm going to feed this into some machine learning classifier. Okay. And this machine learning classifier is going to tell me either it's taken or not taken. Okay. So I'm going to run this with many, many different samples. I'm going to train this machine learning classifier. And now that it's trained, I'm going to use it during the attack, right? I'm just feeding the signal, the machine learning algorithm or classifier is going to tell me whether this is taken or not. Okay. So that's basically what we call a template attack, because essentially in order to train this, I'm using a replica of the original device. It's not the same device, it's a replica of the device, and I managed to actually use it for attacking the system. Okay. So of course you may wonder, what are the right metrics? How do we train it? How many samples, et cetera, et cetera. There's no clear answer, obviously, for this. This is part of the research. People are using correlation, people are using machine learning, people are using different distance metrics, similarity metrics, et cetera, in order to do this comparison. But of course, given that AI is becoming so prevalent and popular these days, most of the attacks these days on templates is some form of machine learning based attacks. Okay? That's kind of it. Thank you. Any questions? So let me give you an example. This is an example of how they attack an open SSL constant time blinded RSA. So this is this constant time blinded RSA means that this particular implementation of RSA is not vulnerable to differential power analysis or simple power analysis. If you do 0 or 1, they give you exact same signal. They actually design it that way, but still they show that they can attack this using template analysis. How do they do that? So, I mean, that's the same old, RSA. It's a little bit different than what you get normally. So this is kind of like, the same kind of main loop for RSA algorithm. The difference is that there is a tiny bit of difference based on the key. And this key is kind of like, looking at, some multiplying based on some bit numbers. Same idea of square multiply and multiply alone. And then what they found was essentially they can look into like very particular parts where the actual this multiplication is happening. So essentially this is the part that's the actual multiplication is happening. And they run it with different inputs, okay? So they run it with when 0 for 0 and 1, and these are two different devices, device A and B. And as you can see, they can essentially like, the red ones, let me actually change my color. We see that the red ones are kind of like, matching each other. And the black ones are also kind of like, matching themselves. So what this tells you is that I can train on device A, right? So what I would do is that I take device A as my training device. I'm going to run this with, when the key is equal to 0. And I'm going to run this when the key is equal to 1. And I'm going to get this red signal and this black signal. Okay, so this is how I know that which one is 0 and which one is 1. Then during the attack time, I need to attack it to device B. So what I'm going to do is that I'm going to collect the signal and see whether it's similar to device A, 0, or whether it's similar to 1. Okay, so this is some form of a signal processing analysis that they do, and they can find whether this is equal to 1 or whether this is equal to 0. Okay, so that's kind of the idea. The view, again, if you're actually looking to this is very similar for different keys. But the tiniest difference that they can find basically at this point here is really, you see very, very tiny differences. And based on like, some large data analysis and some large data averaging, they can find this tiny bit of differences, right? That's kind of like what they're doing with their attack. All right, they actually measure it on real systems, including like, real cell phones and so on. And then they show that they can actually successfully attack the systems. Okay, any questions? Cool. If you're interested to know the details of it, definitely recommend going through their paper and learn a little bit more about the constant time Montgomery multiplication. This is slightly different than the regular multiplication that we have for RSA. The difference is that either if the key is equal to 0 or 1, you kind of get the similar signal. If you actually look into this, the signal is really, really similar. It's just a tiny bit of difference that you can actually capture. Okay, so it's not like, you do a square multiply that I showed you before. If I actually go way up, if you remember this one, there was a huge difference between when you're doing this square multiplication versus when you're not doing this square multiplication. So this was the same RSA code, but this is not the constant time RSA code. So that's why I'm saying from like, 90s or early 2000 to 2017, which this next paper was published, there are actually algorithms that, are resilient against side channels, but still people have shown that there are ways to look more deeply into the system implementation and still you can extract the signals. Okay. So going back down. All right, any other questions about side channels? Okay, let's have a quick break and then we come back and then we continue talking about this. All right. Okay, so to summarize, what I showed you is, by systematically analyzing the code, one might extract valuable information about the design, the data, the instructions, and they can use things like simple analysis, differential analysis. They can go one step further and do template analysis, and they can use a variety of different signal processing or machine learning algorithms in order to kind of extract even more information and launch a more powerful attack. Okay, so this is kind of like the state of the art in terms of signal processing. I'm going to talk quickly about various different ways of doing this. So for example, for signal analysis, you can look into the time domain signals. You can look at the frequency domain signals. There are a whole bunch of works that kind of look at some form of an intermediate analysis, wavelet analysis. All those things is possible. As I told you, side channels at some point becomes more of a signal processing problem rather than anything else. So there are a whole bunch of innovation that is happening at that side of things that actually fuel into launching more powerful attacks on signal processing. Usually, most of these attacks require some form of pre-processing, normalization, reducing the dimensionality, removing noise, and all those things. Again, similar to the way that we are analyzing things like speech, we are analyzing RF signals for receiving the signals. All those things you can apply to physical side channels as well, because at the end of the day, your physical side channel is really kind of an RF signal or a speech signal. Okay, so anything that you do with those type of signals, you can do the same thing for your side channel signal or your time series. And not so surprisingly, these are very active area of research, right? So how do we use things like ChatGPT or large language models to kind of collect things? They are actually directly transferred into the way that we can also handle side channel signals, unfortunately. Okay, so it means that this problem is actually getting more and more pronounced as we are actually increasing our ability to extract more information from complex signals. So I'm just, a few different details. For processing phase, we usually do some form of dimensionality reduction. We do some normalizing. We do some noise removal. Alignment and synchronization is really a big problem in side channel analysis because you have lots of these samples and you want to do averaging, so you need to kind of come up with algorithms to synchronize these different samples. For example, if you go back here, you see that they're actually looking at this part of the signal, but in order to really find the correct beginning and end, what they're really doing is they're looking at this part of the signal, and they found that from this point to this point, there is a constant time, okay? And they cannot really find this point, but what they can find is this point, because this point is really simple. They can run some thresholding or some filtering in order to find this big jump, okay? So there are these kind of tricks that people do use in their attacks against using side channels, that you find different filtering, you find pre-processing, and so on and so forth to attack the system. Okay. So going back down, so synchronization and alignment, being creative how you do that is very important. So what are the main challenges in side channel signals? From the attacker's perspective, what are the main challenges? The interferences is a big problem because when you're collecting, for example, power signal, you're not collecting the signal only from the device or from the CPU. Usually this device is part of the bigger SoC, and this SoC have various different things. For example, this is your CPU that you're looking at, but there's also a network chip, maybe there is a memory, there's an IO and all those things, right? And these are the things that all happens in parallel, all right? So for example, your IO might be, sending and receiving some commands while your CPU is kind of running the AES algorithm, right? As a result, if, for example, I'm collecting the side channel signals using some form of an antenna here. So if I'm looking at this side channel signals that I'm receiving here, I'm not just receiving it from the CPU, but I'm also receiving it because of the activities of the IO or the activity of the memory and so on. So there's an interference that is happening. So what I need to do is kind of, as an attacker, I need to be able to kind of differentiate between the signal I'm receiving from here, or doing some form of a modeling on the background or removing the background. There's all the other ways, including like adding a second antenna that kind of collect these signals, and then I differentiate these two signals. So there are a whole bunch of, as I said again, these are more of a signal processing, wireless communication problems that we are really dealing with here. Okay, so that's one thing that we need to deal with. Even on the CPU side, you may not run just one application, right? You may context switch between different applications. You might have a multi-core system. So even if I manage to just collect the signal from the CPU, I'm collecting multiple different applications, right? So I need to kind of figure out how should I deal with the interference, okay? That's number one. The second is what we call device variation. So I talked about, for example, template analysis, right? So I told you what I can do is I have device A and device B. What I can do is that I can do all this analysis that I want on device A. For example, I know the key, I know the message, I know the ciphertext on device A, because I'm the one who is the owner of device A. And then based on that, I'm going to build a model. Then I'm going to take this model and apply to B. Here, I don't know the key, so I want to find the key. So I only see, for example, M and C. I'm going to feed this M and C into my model, and hopefully I can find the key, right? So that's kind of the idea of a template analysis. But here I'm assuming that A and B are kind of interchangeable, right? So whatever I see in A, I'm going to see the exact same thing on B. But that's not happening in most cases. Why? Because there is a process variation between these two, okay? And this variation is because, why actually we are seeing, for example, power side channels, because of the switch, right? So if I build two different hardware, they're not going to be exactly the same, right? Even they should be the same, they're slightly different. So the signal I'm getting from here is slightly different than the signal I'm getting here. So there is slight variation in terms of physical signals that I'm receiving. So I need to be able to kind of understand that and being able to remove that, to kind of eliminate that sort of variation in my system, okay? So any sort of template analysis needs to kind of deal with this sort of variation in order to be successful, okay? The third one is some variations during the runtime. For example, if the temperature of the CPU changes, probably the signals will change, right? If the runtime, if the different application changes, the signal will change. So again, as an attacker, they need to kind of come up with the solutions in order to kind of deal with this temporal changes as well. And finally, this is really measuring an actual signal, right? So what you really need to do is dealing with SNR issues, with sampling rate issues, et cetera, et cetera. So as an attacker, still you want to use these things in order to, you want to handle these problems, okay? So why do we care about this? Because on the defense side, you want to kind of make sure that you have these as much as possible, right? Because if you have interference, means that it's harder for the adversary to kind of extract information, right? So you might want to understand perfectly well how the attack works so that any defense that you come up with kind of address these issues and use these issues, at least in your benefit as a defender, right? So I talked about different types of side channels, but let's actually more systematically talk about that. So really the difference between the type of side channel attack or the type of side channels is really the channel that's being used. The examples are the more popular ones are electromagnetics and power, Really, these two are the main ones that are being used regularly. Other than that, there is like acoustic and RF and temperature. There's always a new channel that is being proposed. So one part of the research on side channels is always finding a new type of side channel attack and a new channel essentially. So you see tons of papers that are actually looking at new ways and new channels. Some of the paper readings that we're going to do this week and we're going to present next week is actually about this, that how we can find a new implementation or a specific module in the system and use that as new way of like you're looking at the side channel problem. Okay, so that's one thing. The other major difference is the thread model, mainly the distance. So for example, if you want to measure power or you want to measure electromagnetic side channels, you probably need to be close to the device, right? Because this signal does not propagate like 1 kilometer or 1 mile from the device. Okay, you have to be close. But then there's also this clever attacks that reads the power, but read it remotely. So for example, you're going to see a couple of papers next week that they really read power, but they're not reading power on the device with being close. They're using some form of they're hacking into some sensors in this board, and then they manage to read the power, the leakage basically, or the the relationship between these two. Okay, so essentially, while you for example power or electromagnetic measurements, you need to be close. There are other clever ways that you can, for example, hack into the sensors remotely and then attack the system. Okay, so really what you need to pay attention to is that what is the threat model? Do I need to be close to this device? Are there ways that I can remotely launch this attack? What sort of equipment do you need to use in order to launch these attacks? Do I need a very high sampling rate, really high-end device with really low noise level? Or can I use something more bulky and cheaper and so on and so forth? And then finally, of course, what can be extracted, right? So can I attack an RSA or AES or any sophisticated cryptography algorithm, or is it more of like a simple analysis they can do and so on and so forth, okay? So difference between side channels in summary is the channel that they're using and the kind of the thread model that they're using. Okay, so keep that in mind. So as I said, there are also lots of non-traditional side channel attacks. Examples is like power management units. People have shown that LoRa can be used, RF signals can be used. I think I have one example. Yeah. So this is what we call a screaming channel. This is one of my favorite papers, been published a few years ago. So what they found was this very neat idea. So you have what we call a mixed signal chip, that you have your digital logic, you have your memory, basically here, this is your core, et cetera, and usually in the same core, in same piece of silicon, you also have your analog radio, okay? So think about this as like SBF32, a Raspberry Pi with the radio, these kind of devices. Yeah, question.
Sorry, I can just go back to the previous slide. What is LoRa?
LoRa is a long-range communication. I'm going to talk about that. Yeah. Any other questions? Okay. So you're going to have this piece of silicon that has, radio and it has digital logic on it. And again, examples are just embedded systems like ESP32 that's very popular these days. What they found was, I already showed you that, okay, from here, I can launch a successful power side channel attack, right? For example, if I do RSA, I have like square and multiply, and then I can see square versus multiply, right? So let's say there exists this inherent side channel attacks I can do here, okay? What these guys show is that this information can leak into the radio as well, okay? And if this leaks into the radio, can actually propagate it miles and miles away from the device and can be picked up, okay? So this is actually the signal to give you an evidence that it works. So what I'm showing here is this axis, x-axis is time, okay? And this y-axis is the frequency. And this is a Bluetooth chip, okay? So the frequency range is around 2.4 gigahertz. This is the base frequency of a Bluetooth. And what you're seeing here is that first, the radio is off, okay? So there is no activity on the radio side, and then you don't see anything, okay? And then this is basically, it's what we call a spectrogram. Brighter lines means stronger values, okay? So for example, if I just show you here, if I have a signal like this would be a brighter color in this dimension, okay? I'm showing it a 2D signal, okay? So what you're seeing here is that once the radio gets turned on, then you'll start seeing some form of lines which are spikes in the frequency domain. Okay, you'll start seeing things like that, which is you should see because you're running some applications and you get some signals. Okay, but the interesting part happens when not only the radio is on and transmitting some BLE packets, which it normally would, but then you'll start also seeing that once the AES gets started on the core on here, you will see that in the frequency range of the radio itself. Okay, so you actually can clearly see some different phases like here and here. And then if you go back to the design that we had, if you remember, AES was kind of like something like this, and these were different rounds. And this is exactly what you're going to see here as well. What they did was actually they looked deeper into this and they found that they can actually do some form of a differential power analysis on this. And they can find actually the key for the AES. Okay. So what is happening here is that this part is not new. This is like a same old differential power analysis and so on and so forth. But the part that is new and interesting is that they're doing this on top of the radio signal that's been transmitting, okay? So really what they're receiving here is that another BLE receiver, maybe 100 meters away from the original device, and they still can collect those power signals because the power signal is kind of modulated on top of the BLE signal, okay? And that gives a very strong, a capability to attacker because then they don't need to measure this device, directly. They don't need to kind of like, have a probe here and then measure it. They can actually be way, away from the device, just have a BLE connection with the device, and still they can collect the signal and run this attack. Okay, so that's quite interesting in terms of, how powerful a particular side channels could be. Okay, and they call it screaming channel. Yeah.
I'm sorry, what is the red thing again? Is it the power in the
Which red thing?
the red color of the plot?
So lower, look more. So if this is amplitude, okay, red is here and yellow is here. Okay, so if the color is more red, means that the amplitude of the signal is smaller. If it's more yellow, the amplitude is higher. Okay, so what is happening here is that since everything is red here, you're getting a signal that is kind of like this. Oops. Your signal is kind of like this. Okay, the moments that things start getting yellowish, then you're going to get spikes. Okay, and spikes at these frequencies. So let's say, for example, this is frequency F1. This would be F1. This is F2. This would be F2, and so on and so on. Okay, I'm just plotting the frequency over time. Okay. Yeah.
So the statement is that this particular device, the AES process is done after the radio is being transmitted.
It happens in parallel because you have a core here and you have a radio here, right? And these two are two separate units, two separate modules, right?
And then when they happen at the same time, so there will be a lot of sparks of the power.
Yeah. So basically, what is happening is, so you have, let me show it to you here. So you have, conceptually, you have your CPU here and you have your radio here, right? So what is happening is that this radio is supposed to send BLE packets in and out, okay? So I'm sending this packets, but on the same time, there is some connection between the CPU and the radio to send and receive messages, okay? So what we usually do is that, for example, we want to send some message outside. We usually encrypt this message and then send it, right? We never send it, in plain text. So, oops. Somebody's calling me on Zoom. Okay. So we have the core and we have the radio, right? And what is happening is that I want to, send a message. I want to encrypt it. So what I would do is like, I have the message. I have to run this message through AES. And then I have to then send it to the radio. So I'm going to pipeline this, right? So I'm going to message, byte by byte, I'm going to encrypt it. And then as I'm doing the encryption, I'm also sending the previous packets, right? So these two things happens in parallel. My radio is on, I'm transmitting information. As my transmitter is on, I'm also encrypting things. And that's where that thing going to leak into the radio signal. Does that make sense?
Sorry,
Yeah, go ahead.
Why the radio TX base before the ES on base?
Oh, so at the first you want to, for example, send some headers, do some synchronization, right? So you do all those things. So it not necessarily happens at the same time. What this figure is trying to show is that if these two things are happening at the same time, you will see something like this. Okay.
But just to be clear, you're like sending message 1 while encrypting message 2, and message 2 gets leaked into message 1's sending.
Yes.
Okay.
But again, doesn't matter which message you're sending. What it matters is with this, I can find the key. Once I find the key, then I can decrypt all the messages, right? So I want to run a conventional power side channel attack. I could have just, had a probe here and run the attack directly on the device. I could have done that. But if this device is not close to me, then this method is actually telling me that if you have a BLE antenna far away from the device, you still can launch your power side channel attack because essentially that signal will leak into your RF signal. Okay? Any questions? Yeah, if you're interested, definitely take a look at this Screaming Channel paper. They actually have nice demos. They have the code available. If you want to test it, you can actually test it on your systems. It's not all the devices that are vulnerable to this. So it's not every single device that has radio is vulnerable to this. There's a particular types of devices that has these two mixed up that can potentially leak. But there's enough of these devices that it's a concerning concept. Okay. All right. So there's a whole bunch of others. Your paper readings will be basically around different types of physical side channels. Some of them are actually clever attacks that you can use to combine the actual physical attacks with some remote attacks. So hopefully we can have a nice, presentation next week when we can see all these different types of side channels attacks. Okay. Any final questions about the side channels, the physical side channel attacks on the attack side? Okay. So let's also talk a little bit about how we defend against side channels. So one thing to realize is, physical attacks and physical side channels are not something easily we can kind of eliminate, okay? Because these are coming from physical characteristics of the system. For example, you cannot really stop the system from heating up when you're using it, okay? This is not something you can do. So you cannot really eliminate the root cause of side channel in most cases. What you can do is maybe you can shield it, or you can kind of make it harder for the adversary to measure it, but you cannot really eliminate the measurements, okay? So how do we defend against side channels? Let's see if you guys have some suggestions, similar to what we have discussed before. So probably we should be able to get some suggestions, yeah?
You could do shielding. So
Sure, shielding is definitely one, right? Or for power, for example, you can make sure that your pins are not out, right? It's not accessible easily. So that's one thing. And definitely everybody doing that, yeah.
Well, they will try to mask those signals by putting other interference on top.
Yeah, so you add additional intentional interference on top of the actual signal, and that will kind of mask things. Yes, that's another one. Any other suggestion? Okay.
use randomization again.
Randomization also helps, right? So the same line of masking, but make it more kind of decoupling the signal reception versus the information. That's another one. Yeah. So let me go through them one by one. So you can actually do these things at the software level, pure software level. Okay. So you can make your system oblivious to values. Okay, what does that mean? Remember that, lots of examples that we gave you. For example, the RSA one, we had like if E and then do square and multiply, then else we had only multiply, right? You had something like this. And this is fundamentally problematic for side channels because you have different paths in your program, right? For one path, you have square and multiply. For the other one, you have multiply a lot, okay? But if I had something like this, that I had square multiply here and square multiply here, then this essentially is oblivious to E, because even if I can measure the side channel signals, I won't get any information from the system because regardless of E, I always see square multiply, right? So this is what we call oblivious programming, or generally, constant time programming, that regardless of values, we always do the same thing, okay? So how do we do that? First of all, when you're writing your program, you can write it some way that you don't have this kind of leaky branches. That's one thing you could do. The second thing that you can do is that if you have to really have scenarios like, in one branch, you have a square multiply and the other one, you only have multiply. Maybe what I can do is that I can add dummy activities here. So for example, here I can just square maybe like, 100 and 100. And here I'm just squaring the key. So I'm just using a dummy value, and then square it that one, and then just ignore the value, right? In terms of circuit activity, in terms of switching activity, these are the same thing. But in terms of the actual values and the way that it's propagated through software, I just can ignore this value, right? So I'm going to create a dummy value. I'm going to square it and I'm going to multiply it regardless of E. I'm just going to pick one of those two, right? We call it predicated, computation or oblivious computation, okay? So I can add these instructions to make sure that, it's always constant. What is the downside of this? The downside of this is obviously I'm just running dummy instructions, extra instructions without any use, right? So I'm wasting power, I'm wasting area, I'm wasting performance. But on the other hand, I'm safe against side channels attacks, okay? How can I do that? I can do it at the software level. I can do it at the compiler level as well. So there are actually sophisticated compilers that you write your program normally. They take the program and they add this dummy activities in these branches as you wanted to. Okay, so these are this makes the whole process automated because you don't need to even be worried about this kind of things. Okay, so that's one solution is that you can do. But as I said, the challenge is that you're kind of like this is like adding to the power overhead of your system. The second one is, of course, you can make the leakage less and less, right? How do you do that? For example, Faraday cages is the most prevalent one. You put like a metal layer around your device, and that's block any sort of electromagnetic signals out of it. You can limit the output pins. You can isolate the temperature if the temperature is something that's been leaking. So any sort of things that can help you with limiting the signal leakage could help you potentially with the physical side channels. Just FYI, usually like making this a little bit harder than you think. So either they come with lots of cost or there's just not very effective. So essentially, for example, all of our laptops are generally, there are some metal box around it. So you would think that this is like good enough for coverage of EM signals. But since there are small holes in your metal coverage, there are actually leakages. So you really need a perfect cage if you want to kind of block all the EM signals. Otherwise, the signal will leak outside. Okay. The third one is, as someone mentioned, is adding randomness. So the idea here is that I want to decorrelate the signal, the computation, this should be computation actually. The computation from the physical signal. That is, if I'm doing if then else, right? And if somebody can see this, maybe I do some random activity here and some random activity here. As a result, there's not really any information between the two different paths that can be collected by the side channel, by the attack. Okay. Finally, doing some limiting the physical access, because as I said, most of these physical side channel attacks need some proximity to the device. So if I put this device in this room and lock all the doors and not letting anybody to get into this room, most likely I'll be safe, unless I'm using things like, screaming channels and so on. That's kind of like, another class of attacks. But in most cases, valuable devices, you might want to put it in somewhere that is safe. Okay. All right. So that's it with the defenses. Any questions? Okay. So the final thing I want to talk about side channels to kind of finish the discussion is what we call covert channels. Okay. I kind of briefly discussed this, but I want to talk about it in more details. So first of all, why do we need covert channel communication? The reason for that is for air gap computers. As I said, there are a class of devices that for security reasons, you don't want to expose them to the open internet. You don't want to expose their pins to the outside world. And we usually call this air gap devices, okay? So you cannot really send information to these devices. You cannot extract information from these devices. For those of you who have, interned in these big tech companies, most of your laptops that the company give you are usually air gapped in some sense. The network is usually monitored. If you try to hook up in a USB, thumb drive, everything is encrypted, right? You cannot, for example, copy and paste things when you're on the network of your system, send out files and stuff like that. They're doing it to protect their IP, right? So that, a rogue employee cannot steal information from it. Right? But if, let's say, you are a rogue employee, you really want to steal information from them, what you would do is that you are using unconventional way for communications, and we call this covert channels. Okay, so you usually use this for what we call a data exfiltrations. Right? So the main idea is that I'm going to modulate some physical activity, and I'm going to, decide on some protocol in order to send information. Okay, so let's say, for example, I want to I find this really nice C program in the computers that I want to exfiltrate. So what I would do is that say that, okay, I'm going to transfer this into list of zeros and ones. Okay, and what I'm going to do is that I'm going to write a program on another computer that I have, and this one is my computer. And for example, I'm going to blink an LED here, okay? So I'm going to blink an LED, and I'm going to have like a sensor, a photo sensor that gets this data, okay? So I can blink so fast, and then I can record the data, okay? And then what I'm going to do is that I'm going to say that, okay, I'm going to read this text file. This is essentially the converted version of this C program to this, binary file. And then if I see 0, I'm going to not blink, or I'm going to blink once. If I see 1, I'm going to blink twice. Any sort of protocol would work, okay? And then on the other side, I'm going to collect this blinking with fast speed, and this is going to give me a way of communicating between these two, okay? So instead of writing down zeros and ones and things like that, this is a very fast way of communicating the two different devices, okay? And as you can see, I'm not using any sort of conventional method for communication. I'm using an unconventional method, which in this case is, for example, the light density of the LED, right? But I can do other things. People have shown that you can use fan speed. They've shown that you can use the sound. And they show that they can use, changing the EM signals. All these different things can essentially be modulated. And this modulation could be anything. Could be AM, could be FM, could be on-off keying, could be FSK, BPSK, could be any of these standard modulation techniques that we know and we regularly use. You can do the exact same thing when you run your covert channel attacks in real systems. Okay? So what you need in order to construct a covert channel, you need two devices, right? You need a transmitter and receiver. The data is in the transmitter, the receiver is the attacker's device, right? You need a modulation protocol. You need to kind of agreed on a technique that you're sending zeros and ones. And then you, of course, you need some form of synchronization. That is like, when I'm sending this, this is the time I'm going to send it. This is my symbol rate. If there's any sort of handshaking, this is the handshaking. This is essentially the way that we are having for any wireless protocol. We have this kind of thing. So same idea, like a digital signal processing course. If you take, you can build a covert channel easily. Okay. So how do we measure successful covert channels? There are various different things. Stealthiness is the biggest one. The distance, the bit rate, the bit error rate, the equipment. These are the important factors when you want to see how good or bad a covert channel is. Okay. If I can't send data really, really fast, that's probably a good covert channel that I can build. If I can have a low bit error rate, I can send this without really creating errors. That's another indication that this is a good covert channel, and so on and so forth. Okay. So how do we defend against covert channels? The idea is very, very similar. So essentially, whatever you do for detecting against side channels, you should do the same thing in order to detect against covert channels. Another difference is that since covert channels is an active activity, you can actually try to look for it. You can detect this kind of activities as well, right? So one thing that you can do for covert channels is detection, all right? The last thing I want to talk about is actually what I did for my PhD, part of my PhD. And the idea here is you can use side channels for useful purposes as well. Why? Because all these things that I told you that, okay, there is this additional source, leaking information, somebody can find this and pick up this information, right? So why don't we actually use this information for our own benefit? For example, if I want to check the status of a device, why don't I use side channels to see whether this is the expected behavior of this device or not, right? So for example, I can do it for anomaly detection. So what I'm showing here is the signal on the left versus the signal on the right, okay? And if you compare these two, you will see that there's this tiny bit of additional activity here that wasn't here, okay? This is an indication that this device on the right is being attacked by some malware. So my malware analysis can actually not only just look into all these other things that I said, but can also look into, for example, this physical side channel signals and say that, okay, if I see any sort of behavior other than my expected behavior, then I can find it, okay? So the idea basically here is that I can use side channels to build a ground truth and then monitor the device. So device monitoring can also happen with side channel. So the information is there. Instead of using it for extracting information, use it for something useful, such as, for example, program monitoring. Okay, so that's kind of the idea. To kind of summarize the discussion today, physical side channels are critical vulnerabilities. Traditionally, there've been lots of successful attacks have been happening. People have started to be worried about side channels, but unfortunately, similar to, for example, memory attacks, the attacks get sophisticated, the defense gets sophisticated, but there's an arm race between these two classes of problems. And we talked about defenses, but unfortunately, defense is also quite challenging. Yeah, that's it for today. Yeah, for those who are dog lovers, also like dogs as well. Okay, so that's it. Let me put the participation today. What's it called? Eddie.
Eddie Kern.
What's that?
Why is it Eddie?
It's the name of the dog. It's my friend's dog.
It's very cute dog.
Yeah, it is very friendly.
So,
All right, thank you guys.
It's-